I'm just going to go over a couple practical things and say settled. All right. Welcome, everyone. I am so excited to be here. First in-person event in like forever. Just want to remind everyone of a couple things that I legally need to remind you of. First of all, this is not a class, and so you should theoretically be social distancing, because everyone knows when a professor is teaching math, COVID can't spread. But when an event is happening, like a professor teaching math, COVID can spread. Second of all, there's hand sanitizer here. Hand sanitize before you leave. Keep your masks on at all times unless you're drinking something. We were unable to get a mic. This is like not that many people, but if you're being loud, it will still be hard for other people to hear you. And Professor Slofstra has very generously volunteered his time. So please be respectful, stay quiet, make sure everyone can hear him. That's all I have. Let's get this talk started.
We're going till 5?
We have the room till 5:30.
Oh,
So
okay.
go until 5-ish.
Yeah, so thanks for the opportunity to come in. This is my first day back on campus, actually. I'm not teaching this term. So apologies, I'm probably going to seem pretty rusty with writing on the board and everything. I hope that's okay. So what I want to tell you about is a problem. It's one of my favorite math problems, actually. It's not a research problem I've worked on. It's something I encountered in my research, and I think it's really beautiful. I have tried to work on it. I'm not a graph theorist. It's a graph theory problem, so I don't know what my chances are. Maybe it's something you'd like to work on if you have a chance. As you'll see, it's something that's very elementary in a way. Although it's kind of confounded people for about 30 years. Nobody knows how to prove this thing. It's connected to my research in quantum information. And that's how I came across this problem, although it's just a graph theory problem. And so once I tell you about all the graph theory, then I'll try and squeeze in a bunch of quantum information at the end and tell you the story of how I came across this problem. But that part may get a little squeezed in. I'm looking at my notes and it's getting a little long there. So you're warned about that part. But really what I want to tell you about is this graph theory problem. I should also say I actually came across this problem in part while working with a couple undergraduates as part of URA, so Turner Silverthorne and Luming John, in case anybody knows them. So I'll mention some of the work that Luming and I did that's related in quantum information. Okay, so anyway, what does this talk about? Graph theory, right? We've got graph. What is that? It consists of vertices and edges, right? Which is to say, vertices, they're points, and like that, and edges are things that connect vertices. Just say subset of some subset of subsets of V of size 2, right? So there are a bunch of things connecting our vertices. And I might actually talk at the end about digraphs. We'll see if I get that far. But in that case, we would add directions to the edges. And instead of saying subsets of V of size 2, we would actually say E is a subset of V cross V. So we have directions on the edges. Feel free to jump in at any time, by the way. Some of the talk will be technical, some of it won't. If you'd like to see something, how to fill in the technical details on something, feel free to ask. If you want to try and understand some of the technical details for the technical parts a little better, and you've got a question about it, ask at any point. Okay, so this graph that I've written here has a name. It's called C4 because it's a 4 cycle. Okay, and a graph is planar if we can draw it in the plane, let's just say in R2, without any edges crossing. Okay, so C4, right? This is planar. There's a drawing of it without any edges crossing. And very famously, case 3 is not planar. Okay, so this is the graph of 3, 3, 3. We have two sets of three vertices, and we try and connect them to each other in all possible ways. Right, so that's the graph we want to draw. And this is not planar. Let's just double check, because I just drew it there without making any effort, and the edges ended up crossing in all different possible ways. But if I try and be a little more careful, maybe I could do it. I could connect it this way, so far planar. Then I can try and connect around here, and then this one to here, and this one to here. And finally, I can take this guy here and sneak an edge there, but this vertex is blocked off. So to connect these two, I'm always going to have a crossing somewhere. Right? So you can get as far as having one crossing, but you can't get rid of that last crossing with K33. And there's another very famous non-planar graph. Does anybody know what the other one I should write down is? Yeah? K5. And I imagine for most of you, this just remember your combinatorics class. Yeah. So there's a famous theorem of when a graph is planar. So let me tell you that theorem. First, I need some more about graphs. So given a graph B, we can, let's say our graph is actually just C4, for example. Let's give some labels to some of the vertices. And that is, let's call this one B and this edge E. Okay, so what can we do with this graph? Well, one operation we can do on it is called deleting a vertex. We denote that, so let's say this is a graph G. We call the graph, we get G with V removed. And what does that look like? Well, we take the vertex and we delete it, and then, of course, we have nothing for the edges that are incident to it to connect to, so we delete those two. So we get that graph. And then we can delete an edge as well. So call that G with E deleted. That's a lot less destructive. We're deleting a vertex a lot of the time. We just take that edge out of there. And then the last thing we can do for the stuff I'm going to talk about in this talk anyway is called contracting an edge. Okay, and I take this one denoted by G mod E. And what I do is I look at the edge. Let's say W is the other vertex there. And I look at the vertices on the ends of the edges and I squeeze them together along that edge. I just imagine I have this graph and I push these two vertices together and think about them as the same vertex. So in this case, what I get would be look like this. So here's what happened to the vertices V and W. They become the same vertex. This edge becomes part of the vertex as well. Right? Or you could also think about it just kind of drawing a big circle around that edge of the two vertices and say, oh, that's the new vertex. So one vertex. And then the other edges and vertices, they remain unchanged. Okay. Now it's that. Oh, I continue to say definition. Definition. G contains H as a minor if it is possible to get G, to get H from G by a sequence of vertex deletions, edge deletions, and edge contractions. right? So basically, take your starting graph, and then you can do whatever sequence of these operations you want on it. You change the graph a lot, and any graph you can get out of doing that is called a minor of the graph you started with. Okay? And then it's a fact that if G is planar, and H is a minor of G, then H is planar. And in fact, there's a theorem that tells us when a graph is planar. G is planar if and only if G does not contain K33 and K5 as minors. Okay, now, great theorem, Wagner's theorem. Now, and you've probably all seen it, but depending on what version of it you did in say, a common core class, this might look a little unusual, because first of all, the name is going to be changed. Vertexes theorem is maybe what you've seen it as before. And also, the definition of minors might have looked a little weird. Maybe not the version of minors that you would have saw before. So it turns out there's actually two notions of minors. These are called algebraic minors, and there's also topological minors. Okay? And in topological minors, we allow edge subdivision, but not contraction in general. Okay, so it's topological. Having something as a topological minor is stronger than having it as an algebraic minor. You can get more graphs as algebraic minors. Okay, and then it turns out that like in both types of minors characterize planarity, and there's one theorem for the topological case, that's Kuratowski's theorem, and there's one theorem for the algebraic case, that's Wagner's theorem. And for whatever reason, it's not too hard to see that it kind of has to be the case in this case. You get the same minors in both. Looks like a bit of a coincidence at the beginning, since you have two entirely different notions of minors. Okay. And these algebraic minors in graph theory, they end up being a little nicer characterized things. In particular, if you've heard of the Robertson-Seymour theorem, that's for algebraic graph minors. Okay, so far so good. So hopefully, maybe the next thing will be a little further from home. So, cover of a graph G is a pair H phi such that, okay, so what we need is H to be a graph, and the second thing we need is that phi is basically like a vertex labeling. Okay, so phi is a function from the vertices of H to the vertices of G. So it labels every vertex of H by a vertex of G, such that well, I'm going to need some terminology for graphs. So let me just remind you of some notation. Okay, if V is a vertex of G, then the neighbor set of V in G is the set of vertices W of G, such that, well, we could say it as VW is an element of E, right? Or we could say, we could write this condition and say V and W are adjacent. Whatever we call it, it means there's an edge connecting them. So the neighbor set is all the edges that are adjacent to a vertex. So what we want for our cover condition here is such that phi and g and h v. Well, first of all, we want every neighbor of v in H to be labeled by a neighbor of phi v. And then we want to say actually something much stronger, that the function you get by restricting phi to NHV. So now it'll go from NHV and it'll map into NG phi v by the condition we just wrote down. We want this to actually be a bijection. Okay, so rather than puzzling over this definition, I think it's very easy to understand. If we look at a definition, oh, actually, this is makes me look more competent than I am, which is bad, because you'll feel let down later. This is the graph I want to do an example of. But actually, this takes up too much space, so let's go back to our more compact way of writing K through 3. Like this. And let's give our vertices labels. Let's call the first partition 1, 2, 3, and the second partition A, B, C. What I want to write down for you is a cover of K through 3, just so we can understand this definition. So what I'm going to do is I'm going to make two hexagons. This, one inside the other. And let's mess them up. And then let's make spokes. Make it the outer, and now I'm going to put labels on. So this is my H. So notice at this point, I've written down a graph, but I haven't labeled any of the vertices. I need my function phi going from the vertices of H to the vertices of G, and I'll specify phi just by writing what vertex of K through 3. It should go to beside each vertex. So what we're going to do is, let's see, 1, 1, and then we'll do A, and then I'll do, let's see, 2, 2, and 3, 3. And I guess B, B, and C, C. Okay, let's see if I did it correctly. So for this to be a cover, what we need is that if I take a vertex of H, make sure we got our quantifiers in place over here. This should be for all V in V of H. So in other words, I have to be able to pick for any vertex of H, right? I have to show this condition is satisfied. Let's choose this one. Okay, so this is saying, first of all, if I look at the neighbors of this vertex in H, there are these vertices here. Now look at their labels. It's A, B, and C, right? Those have to be things that one was adjacent to in K through 3, which they are. One is adjacent to A, B, and C. And second of all, it should be exactly the things that one is adjacent to. And that's what happens. One is adjacent to 3 vertices labeled by A, B, and C. If I take A, that's adjacent to 3 vertices labeled by 1, 2, and 3. Right? If I take this vertex, it's B, and it's adjacent to 1, 2, 3. Okay? So what it looks like, actually, I made a drawing of K through 3, but I just repeated every vertex twice. That's kind of what it looks like here. Right? So that's why I said in the description of the talk that you can make a cover where you have multiple copies of each vertex, kind of an informal way of thinking about what a cover is. Okay, so this is a cover. Okay. So now it's an interesting thing about covers. So if we start with a connected graph, well, we know what that means, right? It means that there's always a path between any two vertices of the graph. So the T is connected. And phi is a cover. Then the number k, which is the size of phi inverse b. It turns out this looks like a function of v, but it actually isn't. So this is independent of v. Of v in G, the vertex set of G. And we say that that H is a K cover. Okay, so you can see that's exactly what happened here, right? When we drew this, we had exactly 2 vertices for every vertex of K33. So this wouldn't just be a cover, it would be a 2 cover. Okay, the other thing we say is we say H5 is a planar cover, a planar K cover, if H is planar. And again, that's exactly what we drew here. We drew a planar 2 cover of K3. Now, if you want to, but K5 also has a planar 2 cover. On the other hand, just like there are graphs which are non-planar, there are graphs which don't have a planar cover. K44 is an example. So you don't have to go very far to find does not have a planar cover. Okay. Now, we might like to try and characterize graphs that have planar K covers the same way we characterized planar graphs. And we can get off to a good start with that by saying that if G has a planar K cover, then any minor of G has a planar K cover. The Robertson-Seymour theorem, that is an amazing theorem, not part of this talk, but still amazing, says there has to be like a finite set of minors such that you can characterize having a planar K cover by avoiding those minors. Okay. And we actually know in one case what those minors are. So there's a theorem of Negami, which says that if G is connected, then G has a planar 2 cover if and only if G does not contain one of the list of 35 graphs as a minor. Okay, so it's a little complicated to characterize, But, you know, in the grand scheme of things, 35 is you can get much worse than that. So. Okay. Now, the weird thing about this is that this is where Negami's conjecture comes from. In fact, we do not know a graph which does not have a planar two-cover. Okay, this isn't it. So we do know lots of graphs which don't have planar two covers, right? But for every one of those, it turns out they don't have planar covers at all. Okay? Well, as far as we don't know if they have planar K covers. But has a planar K cover for K greater than 2. Okay? So we don't know a graph which does not have a planar 2 cover, but does have a planar K cover for some K greater than 2. It's either you, well, one thing that's happened is you're planar. Okay? Actually, let me write out Negami's conjecture. So. Sometimes this is actually called the 1 to infinity conjecture. You're going to see why. So if G is a graph, then either G is planar. Okay, that's the one part. Because it has a planar 1 cover then itself, or G has a planar 2 cover, or G does not have a planar cover. And so far, for every graph we know, well, either it's planar, we can determine those ones easily, or it has a planar 2 cover. That's also not that hard to figure out, right? Well, we can do it using, we can figure out if it does have a planar 2 cover, we just have to give the cover. But even if it doesn't have a planar 2 cover, we can show that we can figure that out, but figure it out whether it pays one of these minors. Or one of two things happens: either we know it doesn't have a planar cover, or in some cases we're not sure. There are graphs where we know they don't have a planar 2 cover, but we're not sure whether they have a planar cover. We never found one. You'd have to go up to maybe not so hard to check if something doesn't have a planar 3 cover. You only need 3 times as many vertices as your graph. But how do you check whether something has a planar 1 million cover? Not so easy. So we have some graphs where we don't know whether they have planar covers or not. Okay. Now, what makes this such a beautiful conjecture is how easy it should be to prove this. Because all we need to do to prove this, you think, is show that none of these graphs in this list, these 35 graphs, have a planar cover. Okay, so we could prove Negami's conjecture by showing that none of the 35 graphs in Negami's theorem have a planar cover. So why is that? Well, suppose that was true. So proof, if that was true, then if G does not have planar 2 cover, then G contains one of the 35 graphs as a minor. Okay? And now we look at this and we wrote down over here, right? If G has a planar K cover, let's say one of the 35 graphs, let's say the graph is H. Let's take that in there. So if G has a planar K cover, then so does H. Okay? And if we knew that none of these 35 graphs had a planar cover, then that would be a contradiction. Right? So it wouldn't be possible for G to have a planar K cover. So all we really need to do is just check 35 graphs. Okay. Well, it turns out it's even better or worse. I'm not sure how you describe this state of affairs. In fact, we know that there's just one graph among the 35 that if we were to resolve that case, it would resolve all the others. So there's a bunch in the 35 we already know don't have planar covers. And then there's a handful that we don't know. But if you could check that one of them, there's one in particular that if you check that one, then it's known that all the rest wouldn't have planar covers either. So that Negami's conjecture would be true if it's just one graph that's for the holdup, you think it's probably going to be a really monstrous graph, right? In fact, it has only 7 vertices. Okay, so if this graph A 1, 2, 2, 2 does not have a finite, well, have a planar cover. And what is K1, 2, 2, 2? It's the graph where it's like K and N, but there are multiple partitions now, 4 of them. One with 1 vertex and 3 with 2 vertices. What you do is you connect everything up. You connect everything in one partition to everything in every other partition. So this, let's see, that. Did I get everything? It's okay. Yeah, okay, so it's a little monstrous. The edges are kind of bad, but yeah. I didn't do any favors with this drawing. You can draw it with fewer crossings. So, yeah, it's there's not that many problems out there where all you have to do is show this graph, 7 vertices, doesn't have a planar cover. How might you do that? Well, you've got to try and find something about this graph and then say, look, if you were to write down a planar cover of this graph, maybe this property would also hold for the planar cover, but maybe there's no planar graph with that property. Something along those lines. That's how we kind of are able to prove some of these other graphs don't have planar covers. But nobody's found the right thing to use for this graph. What do you use? There's kind of infinite number of choices. Oh, question? Oh, okay, sorry. I don't get that. I should repeat, questions are welcome if anybody does have questions. And maybe, is it worth writing down on the board? So, unless This has been open for 30 years. Yeah?
How did we come up with the 35 graphs? Could we come up with a 36th one, or is it proven that?
Yes, no, that's the smallest possible number. Once you can start finding a list, once you get to a finite list, as long as, so there are, technically you could write down a computer program that would make you a minimal list at that point. The computer programs are like, they're polynomial, but not necessarily the smallest exponent, like n to the fourth for checking if something's a minor or something else, so add on a couple more, maybe n to the sixth or something, would probably be good enough to be your minimal list. But, you know, as long as your graphs aren't too big and your list of graphs isn't too long, that's okay. So, where this comes from is actually, it's quite interesting as well, because it turns out the Planar K Covers, that's the same thing as being able to draw your graph in the projective plane. So you know you've got the regular plane, R2, and then the projective plane is, you know, it's a non-orientable version of the plane that kind of comes up in projective drawing and things like that. So it's something to look up. Even Wikipedia has a pretty good symbol of projective plane if you want to see it. So how can we construct a projective plane? One way to construct it is you start with a sphere, and then you identify pivotal points. Okay, so basically you think of this point being the same as this point being the same as this point. Okay. And that gives you it's called a projective plane. And so if you can draw something in a projective plane, then it gives you a version of the drawing of the graph where you get two copies of every vertex on the sphere. And drawing something on the sphere, in terms of for a graph, is the same thing as drawing it in R2. So if you have a drawing of something in a projective plane, then you can get a planar K cover. And for connected graphs, it goes the same, the opposite direction as well. So if you have a planar K cover, you can actually draw it in a projective plane. And that's what Negami proved. And then maybe it should be kind of makes sense. We can figure out what the minors are for embedding in the plane, then we can do it for other things that are like the plane, including the projected plane. I don't know if that's reasonable or not, but it turns out to be the case in the projected plane anyway. Yeah. Any other questions? It's a great question. Okay, let's pivot a little bit. I want to tell you about where I came across this problem. So for a while I thought maybe I had an approach that would be able to solve this problem. Turned out not to work. Not in an interesting way, actually. And where I thought where I encountered this problem, and maybe I thought there would be some ideas to solve it as well, came from quantum information. So I'm just going to tell you a little bit about that, not the whole story, I think, given the time constraints. So one more thing before we kind of move on to this conjecture. There's a wonderful paper where I learned about this for the first time called 20 Years of Negami's Conjecture. It was written about 10 years ago. Okay? So you can keep track of how long the problem's been open. And it has a list of those 35 minors if you'd like to look. Okay? So I want to talk about, I guess it doesn't hurt to start mentioning digraphs now. So from now on, we'll think of to use a digraph rather than a graph, which just means we're going to slap directions on the edges whenever we draw a graph. And we also want to pick a prime number. Okay? And I want to think about the following question. Well, we'll need one more thing. We'll need a function from v of g to zp. Remember, this is just this set of congruence classes mod p, right? When we add them, p, I. There we go. So when we add two numbers in CP together, we then take their residue mod p, and that's what we think of as a result. Okay. So I want a function from the vertices to ZP. So we're going to label every vertex by element of ZP. Okay, and what I want to ask is, for this graph, question, is there function x, let's say, from the edges of G to ZP, such that basically what I want to say is that when we sum over the edges, so this is for all vertices in G, when we sum over the edges which are in the neighborhood of this value, we get b of v. But now in a diagraph, I actually have to incorporate incoming and outgoing edges. And that's important here because we're going to change the sign. So I want to say actually the sum over e such that the source of the edge is equal to v. And we'll say we'll sum over those edges with a positive sign, and then we'll subtract the edges where we have an incoming edge. Okay, so if I write an edge, this would be the source, and this would be the target. Okay. So if you have an outgoing edge, you treat that with a positive sign, and if you have an incoming edge, you weight that with a negative sign. And what we want is the sum to be equal to b of v for all v. Let's just try this. P equals 2. We can try it on C4. Okay. So, and I need to tell you what the function b is. So I label every vertex. Okay. Let's just label it by 1, 0, 0, 0. Actually, why don't we start with this? We label them by 0, 0, 0, 0. Can we do it in this case? Well, I need a direction as well, but maybe you can see the directions don't matter in Z2 because +1 and -1 are the same thing in Z2. So we won't worry about those right away. What should I label the edges with to satisfy this condition? Yeah?
All the same.
Yeah, all the same. So I could do all zeros, or I could just do all ones. We work 2. That's a little more fun, right? And we see 1 + 1 = 0, 1 + 1 = 0, 1 + 1 = 0, 1 + 1 = 0. Now, if I change this to 1, okay, this won't work anymore. So I could maybe start off with a 0 there, and then go to 1 here. So now 0 + 1 = 1. And now I need to get 0 here, so I need to put a 1 down here. And then I need to get a 1.
That wouldn't work.
Pardon?
That wouldn't work, right?
Yeah, this one doesn't work. We just 0 + 1, right? We broke that. So we can see that we're not going to be able to solve this one. So sometimes we can solve the problem, sometimes we can't. Also, the prime we choose can matter. So let's say instead of 0 there, I put 1 there. That works for our, that works now, right? But if I go to p = 3, and I go 1, 1, 0, 0, and now I need the direction. So I don't know, we can orient it like this. Okay, so outgoing gets a -1. Maybe I should have oriented it the other way. But we could do 1, 0, right? So incoming, yeah. Oh no, incoming gets, I did it right. Outgoing gets a plus. Okay, so I could do 0 and 1. That works at this vertex. It's 1 - 0. And then now that contributes coming in a -1, so we need a +1 to cancel it out. Right? You can see this is like a flow problem. We got a 1 incoming, and we need a 1 outgoing to cancel it out. We just do everything mod p rather than over the integers. And now we got a 1 incoming, so we need a 1 outgoing. And if I did this right, this is now a -1, doesn't match the 1 there, right? So you can see this doesn't work, even though it did work when we did it over p equals 2. So and you can also see why we need the directions for the, once we go up to higher planets. Okay, it turns out, here's a fun exercise to show. If G is connected, then the answer, then, let's say then x exists. If and only if the sum over V of BV is equal to 0. And keep in mind that's equal to 0 and ZP, so 0 mod P. So you can see why 1 plus 1 is 0 mod 2, but not mod 3. That's what happened when we went to a p equals 3. Now, I want to tell you about a little bit about non-local games. So in a non-local game, we have 3 parties. We have a ref, and we have 2 players. So usually we call them Alice and Bob for A and B. So in this game, what happens is the referee picks a vertex at random, let's say, and sends it to Alice, and picks another vertex and sends it to Bob. And then what they have to do is they have to reply with questions, so with answers. Okay, so basically they have to send back a function from the neighborhood of V. Oh, sorry, I don't want the neighborhood of V there. I want the incident set V to ZP. Okay, so what's the incident set? That's the I of V equals the set of edges such that the source of E is equal to V, or the target of E is equal to V. Okay, so it's all the edges that are connected in one way or the other to V. So what we want is actually an assignment for all those edges from ZP. And Bob has to send back the same thing. And they can't send back any function. The function needs to satisfy that the sum over edges with outgoing edges weighted by 1 and incoming edges weighted by -1. That needs to be B of V. Oh, I guess, let's see, it shouldn't use, oh, of course. It's going to use X and Y. There we go. Okay, and that's X. Okay, and we want the same condition here for Y. Y minus sum over Y is equal to B of W this time. Oh, and that should be W. There we go. Okay. So these things come back to the ref, and the referee decides whether they win or lose. Okay, and they win if and only if XE is equal to YE for all E in the edges incident to V intersect W. Okay. So when you think about this game, it's like a test. Your friend says, I can color the edges of this graph that we're working with to satisfy this condition. And you say, well, I don't believe you, but I don't want to actually check this whole condition. I'm really lazy because this isn't that hard to check. Okay? But I'm so lazy, I really don't want to check more than one vertex. So what you're going to do, find another friend, and I'm going to ask you to independently, okay, what you should assign. I'm going to pick one vertex for each of you, and I'm going to ask you independently what color should go around that vertex. Okay, and then I'm going to check that your answers satisfy the condition I want for those two vertices, and that you gave the same answer. Now, if you're doing that in the same room with the two people that are answering, right? So there's two cases in the game, either, well, three cases really. So this might be empty, like if one player gets this vertex and another player gets this vertex, there's nothing to check at the end. Okay? So then they just win automatically. The other possibility, one of the other possibilities is they get the same vertex, so then they literally have to get the same answer for all edges. And the other possibility is that they get a pair of adjacent vertices, in which case they can get the same answer on that edge. But these edges, they can get different answers. Now, if they're in the same room, all Bob has to do is wait to hear Alice's answer and then pick his answer to match on either all the edges if they got the same vertex, or on the one edge that wasn't common. So they can always play this game. But that's not what you do. What you do is you make sure they can't communicate once the game is started. Okay, so this is what makes the game difficult for Alice and Bob. You put them in separate rooms, and then you pick the vertices that they're going to see afterwards. So they won't know when Alice gets her vertex, she won't know whether Bob is getting a non-adjacent vertex, which is free pass, she can say anything, or is getting an adjacent vertex, in which case they have to agree on this edge, or getting the same vertex, in which case they have to agree on all of the edges. So what you can show is that with this no communication condition, where they can't communicate while the game is in progress, Alice and Bob can win with probability 1. Okay, where do probabilities come from? Well, so in some cases, they may not be able to win perfectly. Like they may not, so if they have a coloring of the graph, they can just take that coloring, write it down, and go to two separate rooms, and then reply with what the coloring is. But if they didn't actually know a coloring, then what they might try and do is just guess what to do. And they'll win with some probability. Sometimes they'll get lucky. Maybe they'll get asked to non-adjacent vertices, and then they always win in that case, for instance. And sometimes they'll get off. Right? So there's a probability that they can win, and you can look at what is the best strategy that they might use, call that the optimal winning probability. Okay, so that optimal winning probability is 1. In other words, they will be able to always answer, always succeed in this game, if and only if X actually exists. So if you're really lazy and you only want to check one vertex, or really, I guess, two vertices at a time, you can play this game and at least you have some probability, if X doesn't exist, you have some probability of catching up, some non-zero probability. Okay, so if that's good enough for you, then you can get away with really lazy. That's the application, I guess, of these games. Now, the weird thing is that in physics, this can't communicate condition is really funny, okay? Because it turns out there's something called entanglement, where you can have physical systems which can't communicate at all. In fact, you can put them on, let's say, very far apart. One experiment that did this on Greek islands, okay? So different islands in the Mediterranean. And then you can ask for their answers so fast that no time would have to travel. There'd be no time for a signal to travel from Alice to Bob, or vice versa, without breaking the speed of light. Okay, so that's a reasonably good definition of can't communicate. Faster than if you can travel faster than the speed of light, you could communicate in that situation. But okay, so so despite this, although you can have these physical systems that can't communicate, they can be entangled, which means that they can have correlations that you can see between the systems when you do measurements on them that shouldn't really exist from our classical intuition, although they're perfectly fine from the point of view of quantum mechanics. So sometimes the mystery of them can be a little overhyped, and we have a theory that perfectly explains them, just not the theory that we had 100 years ago. So what you can say in this case, for t equals 2, and G equals K through 3 or K5, even if the sum over BV is not equal to 0, right? In which case there's no actual x that exists. There is a strategy using entanglement that can win this game. So, it's kind of interesting fact. You say that there's like a quantum x that exists. You can actually make that kind of precisely in that way. And the theorem of Archibald okay. In fact, if the sum over b is not equal to 0, this is for the p equals 2 case. Then it's possible to play perfectly with an entangled strategy if and only if G is non-planar. Okay, so if you're non-planar, so in other words, if you hang one of K3 or K5 as a minor, there's actually a strategy to play perfectly with entanglement. If you're planar, unfortunately, whether you can play perfectly or not is down to whether the sum is equal to 0. Yeah?
When you say play perfectly or win the game, do you mean win with probability 1?
Yeah, exactly. Yeah. Okay, so this is where I get to mention the work that Louvain did. So nobody really knew what happens when t is greater than 3. And there's a lot of stuff we still don't know. But what we can say there are graphs where it's possible to play perfectly with entanglement even if, just to emphasize here, even if the sum over b of b is not equal to 0, okay? For all p. And it turns out this is like not having a planar cover, because what you can show is that if G has a planar K cover, then and just for simplicity here, I'm going to now assume that the sum over BV is equal to 1. That's nice because 1 is not equal to 0 for every B. Okay, so I don't have to worry about being somehow 0 on some of the B's and not others. Okay, so if G has a planar K cover, then it's not possible to play perfectly with entanglement for any p less than k. So you can see now where Negami's conjecture comes in. So if we had a graph with, so we have graphs with planar 2 covers, in fact K33 and K5, which you can play perfectly with p equals 2. They have planar 2 covers, right? But having a planar 2 cover doesn't put any constraint on them. Well, hold on, for p less than k. Excuse me. There we go. I think that's better. Okay. So we have a planar 2 cover. It turns out you can't play these perfectly for any p larger than 2. You can only play them perfectly for p equals 2. On the other hand, we have graphs where it's possible to play perfectly with entanglement for all p. Okay? So it kind of looks like if you can play perfectly for p equals 2, it's like having a planar 2 cover. And if you can play perfectly for all p, it's like just having not having a finite cover. If you had a finite cover, you would be able to you wouldn't be able to play perfectly for some. It turns out you could make this even a little more analogous here by making an if and only if, but you've got to replace planar K covers with what are called pictures. So there was part 2 of this talk. So we start with what a picture is. You get a relaxed condition of being a cover. So you can make this an if and only if. And this is where my optimism about being able to solve this conjecture came in. At some point I thought, oh, pictures and planar covers are so similar that probably exactly the things that you can play perfectly with, that being able to play a game perfectly with entanglement for some p is exactly the same thing as having a planar K cover. Okay? And then we have a situation where, for the graphs that are planar, we can't play them perfectly in p equals 2. For the graphs that have a planar 2 cover, we would be able to play them perfectly for p equals 2. And for the other graphs, we'd be able to play them perfectly for all p. And it would help us solve the conjecture because maybe we'd have a method to show. What would you have to show? You'd have to show for k 1, 2, 2, 2, 2, 2, 2, 2. 1, 2, 2, 2. There we go. Okay. You have to show for k 1, 2, 2, 2 that it has a perfect strategy for all p. That would do the trick. Unfortunately, it turns out there are graphs which, although they don't have planar covers, they do have planar pictures, and that ruins this. So pictures and covers aren't comparable. But nonetheless, the weird thing is that we still are in the same situation as Negami's conjecture, where for every graph we know, it's either you can play it perfectly for, you can't play it perfectly if p equals 0, or you can play it perfectly if p equals 2, but not for any higher p, or you can play it perfectly for all p. That's the only situations we know so far. So you could say maybe there's a quantum games version of the Negami's planar cover conjecture, where so it's not a planar cover conjecture, but it is a 1 to infinity conjecture, right? That for any graph, either you could play it perfectly for this game perfectly for all p, or for p equals 2, and that's p equals 1 and 2, and that's it, or p equals well, p equals 1 would be you can't play it perfectly unless the sum of p is at p equals 2. Okay, I'll stop there.
If you want to pop here.
Oh.
So I do have a question about where we use the primality of p in either the problem or the strategies.
Yeah, it actually doesn't really matter so much, but if you want to do the exercise, it would be helpful to know, I don't know, did anybody think about when x exists? You might have noticed, do we still have the condition? I guess it's gone now. Let's write it down again. Sum across so sum of the edges we have xe, and other of the edges we have minus xe, and that should be equal to d of v. It's a linear equation, right? It turns out if I wanted to write it like with matrix, you write down the incidence matrix of the graph and set that equal to b. That's the equation you're trying to solve. So the question is, can you solve a linear equation? And that's easier to do over a field than over a ring. Yeah. So just for that reason, but really, actually, I think everything is still true when it's not prime. And there's kind of as kind of an example of when you're on uncertain ground, some people will just kind of we cling on to things that are familiar just in case we need them later. Yeah.
Exactly.
Yeah. But so far, we don't really know any reason to stick with the prime.
Can you elaborate a little bit more on what the entanglement strategy means, either mathematically precisely previously, or just like what changes about the game when you have an entangled strategy?
Yeah, that's a great question because I have an answer ready to go on that one. So, okay, yeah, and it fits in just with writing down that equation that I wrote down. So perfect timing. Okay, so there are two ways to answer that question. One is we could write down, according to the rules of quantum mechanics, what it would mean to have a strategy for this game. Probably we should start with what a strategy would look like in the normal intuition for such a game, and then maybe go to quantum mechanics and so on. And there's a number of courses you can take here that you'll learn about stuff like that. So PMath 343 is the one we have in PMath in, I forget the number, 47 maybe is a quantum computing course. Okay, but I want to give you actually an algebraic answer. So it turns out you have a quantum entangled strategy. So if I think about this equation, Ix equal to b, let's make the p equals 2k so I don't have to worry about signs, right? If you think about what it means to have a solution to that system, okay, I've got to fill in with the x's with numbers from z2. Okay, I could do that with like working over z2, or if I didn't, like if you wanted to give somebody this problem and they didn't know about z2, you could actually just give them the same problem with plus and minus 1. Okay, that's isomorphic to z2, and then the equation would look like product over e in ib, which xe is equal to minus 1 to the b. That's the system of equations. So what we actually want is to have an entangled strategy. So roughly speaking, a strategy would be where we replace like a probabilistic strategy used by random variables. And in quantum mechanics, there's also a notion of random variables, and they are self-adjoint matrices. And if they're plus minus 1 values, then they're self-adjoint matrices with square root of 1. So, and then we just want the same equation to hold on those matrices. So it's if and only if there are matrices xe for all e in E and G, such that so we want them to be self-adjoint, and we want them to square to the identity. That's like saying that all the eigenvalues have to be plus or minus 1. So if it's self-adjoint, then it has to have real eigenvalues to be diagonalizable, which means that the eigenvalues have to be plus or minus 1. And 2, we want this condition, the product over E and IV, XE, should be minus identity to the B. Now there's a couple of things that need to be fixed here. So far, actually, this seems reasonable except for one problem. In the game, Alice and Bob, well, let's just take a look at Alice. She could use the XEs as part of a quantum strategy, but she has to be able to return values for all the E's incident to any given vertex. And it turns out that puts on a really special condition in quantum mechanics. You want to measure, so the weird thing about quantum mechanics is you could have different things you could measure, let's say, and random variables represent them. But you can get uncertainty principles where measuring one means you get uncertainty in measuring the other. Okay? And there's a lot of philosophical stuff you can say about that, but suffice it to say that if we have jointly measurable quantities, then what we really want to happen here is the random variables commute. So this is a group commutator, X, E, XF, XE, XF. Now, what edges should they commute for? Well, if you make them commute for all E and F, then the fact that they're matrices doesn't matter, you can jointly diagonalize them, and then you just have a solution to the classical problem on each diagonal entry. So if you make this for all E and F, you just back to the original problem. So it turns out what you want to do is just for E and F in IV, sum V. So in other words, you have variables now, need some graphs. We're using C4. So this would have like 4 different variables. And then you would say, like, these 2 variables have to commute. Well, unfortunately, oh no, it's okay. Yeah. So this variable doesn't have to move this variable because they're not incident to the same vertex. So that gives you a little more leeway on your matrices here. If you could find solutions to this system of equations in matrices such that aren't one-dimensional. There aren't one-dimensional solutions. There's one more thing, technicality. This part here. So actually, one of the many outstanding mysteries we still have, I said that Lu Meng and I managed to find graphs where for higher P, you change this to no more self-jointness, then they're unitaries of order P instead. But we can only, so we can find graphs where this system of solution equations doesn't have a solution in plus or minus 1. So these do. But they're not actually in matrices, they're operators on number space. And we still don't know whether there's graphs where you can make these finite dimensional for all P, or any P actually. Yeah, so that's one of the many things we still don't know. I think I got everything. And I guess the only I think the algebra of this is very nice. It might be a little unsatisfying. There's no mention of what entanglement means in there. But it turns out there's kind of a standard way to think about what you can do with entanglement between 2 players if you have one of these. And one thing that can happen is that you can make, if somebody does a measurement here, you can make it perfectly correlated with the measurement that happens here, as long as they know to do the same measurement. And the weird thing about that, like, it's not so weird. Imagine you've got somebody who is, I don't know, they're traveling around to different offices, and they notice that 2 people at, this person at this office has the same sock color as this person at this other office. So the measurement of sock color is always perfectly correlated between these 2 people, even though they can't communicate. That doesn't seem very strange because maybe, they are married and they just coordinate their sock color in the morning and then they go off to different offices, right? You wouldn't make some kind of X-Files show around that premise. But what happens in the entangled state situation is that they don't know, you get perfectly correlated even though the measurement that you're going to make isn't fixed ahead of time. So it's a little more, and of course it's got to be more than that. That kind of just a story by itself. You can imagine 2 people who are perfect clones of each other still could be perfectly coordinated at the end of the day. Make a list of all the measurements you can make and so on. So you kind of have to go into the math of why that's unusual, what it's meant by measurement and so on. But I think it starts to seem surprising. They don't know what measurement you're going to make. You show up, you do some kind of really random measurement. I guess, is it fair to say the position they're in would be an example of a measurement? It'd be really hard to perfectly correlate everything about the 2 parties. Anyway, that's kind of like a story. The math, if you have a chance to learn the math explains it better. So that's what you do. You have your 2 players play with this matrices, thinking of them as random variables, and using one of these entangled states allows you to perfectly correlate between the 2 different sides.
Okay, no more questions? All right, thank you so much for coming.
Yeah, thanks for having me.
Absolutely fantastic.
if anyone wants to try the exercise.
Oh yeah. I think that
Thank you all so much for coming. This was fantastic.
was